All right. Hi, we're recording my office hours. We just went over one, which I guess we can say again. The reason why one works, why helium doesn't exactly fit with its position, because in contrast to all the other like noble gases, they have an electron, it doesn't have a configuration of ns2 to like np6. So it's out of place in group 18 in that way. But you could also argue that the element helium represents the end of period one, which is chemically and it is properly classified as a noble gas. So in that sense, it fits. Though it could also be said purely on the electron configuration that it might be group 2. But helium is not a metal because it's not like, it doesn't have any similarities with like beryllium. Neither is hydrogen a metal, but when the group 1 elements are referred to as the alkali metals, hydrogen would not be included. So helium would also not be included from all the other metals. So in that way, it would work. So did you have a hard time understanding 2 as well?
What I didn't get was trying to find like another resonance. And then also like, what does isoelectric mean?
Isoelectric?
Yeah.
Isoelectric. Okay, well, first let's focus on the what's it called? The resonance structure. So I'm going to try to give permission to you know what, we're just gonna draw. We're just gonna draw it out. So let me just quickly pull up a screen. Oh. Okay. Pull something up. I have to do the really fucking scuffed way. Okay. Share screen. But it makes sense so that you could listen and then you can do that on. Okay. So, in what ways do you see the molecule?
Like how I drew the Lewis structure?
Yeah.
So I did N with like the lone pair triple bonded to the carbon, and then a single bond between the carbon and the fluorine, and then that has like octet.
So, so like this. Oh, I do not like that.
No. Oh my God. I forgot we were doing that.
So like this.
Oh my God.
Yeah.
And like this.
I have this like server study together thing, and it's like that, like it's a whole community. Like right now, there's like 30,000 people online.
Like that?
I could create a private channel.
Yeah, but there's one too many lone pairs on the end.
Yeah, I get that. Just ignore that.
Mm-hmm.
Okay, it's fine. I'll just
Sorry
create
for the
my own
noise.
private
I
channel,
came
and I'll
into a
just sit in
script.
there alone, you know,
I came into a site one. Okay, so you want to find out what else would fit here?
No, like I didn't understand why he wanted us to have another resonance.
Well,
or like a resonance at all.
Well, he wanted to represent the fact that in these things, bonds shift around a lot. They bounce back and forth. Like this is primarily what it's going to be, but occasionally it's going to be like this.
Mm-hmm.
And very rarely, and I mean really rarely, it's going to be like this. It's gonna be very rarely like this. Fluorine does not like this at all.
Mhm.
I do not believe you.
And
Not on my computer.
you can even take it all the way in that it's like this. This is very unlikely and is never going to happen, but
Mhm, mhm.
this could also happen. So does that help solve your answer question?
Yeah, yeah, I got it. And then, so what is isoelectric?
Isoelectric is, it's like having the same number of electrons in, or the same electron structure. I'm assuming you want an example.
I mean, he said CO2, but I just didn't understand how that like relates.
Let's see. So isoelectric are species with the same electron configuration. So like it would be like having the same as 1s2, 2s2, 2p6.
Oh, okay, gotcha, gotcha.
Yeah. It's like those having the same values.
Okay.
Okay, let's see. So I'm assuming you want to go on to the next question? Or,
I mean, I
okay,
think I'm good unless anyone else has like other questions.
what y'all want?
I had a quick question on isoelectronic species.
Okay.
So I understand that in the example you just drew, the isoelectronic species would be carbon dioxide because nitrogen is 5 and fluorine is 7, which equilibrates to the 6 and 6 for oxygen. But he gave us an example in class, formal fluoride. And I was wondering if you could go over that because I know that carbon dioxide wouldn't work for that, and I couldn't figure out what else would.
Or more what?
Like the C double bond O and then a single bond to fluorine.
Oh. And C double bonded fluorine?
No, single bond to fluorine and there's an H.
Oh, okay.
Yeah.
And what exactly about this is confusing?
How would you determine the isoelectronic species for this?
Well, here we want to focus on this guy because he's the center atom. Carbon would be, let's look at the periodic table and notice that carbon is in the 2p group, and he is 2p. He's 2p4. So the carbon on its own is 1s2, 2p4, and that's him on his own. And these bonds help bring him up to 2p6. Because he's evenly maxed out and he's balanced out because he has all the bonds that he likes to be happy with. You'll learn later on that molecules want to fill their whole octet stuff, and that's the whole sort of electronegativity stuff and electron affinity. Does that make sense?
Yeah, I get that part. So then how would you actually figure out like what the species that's isoelectronic is?
You count your electrons. You usually get, I'm pretty sure he'll give you like a periodic table. From there, you just need to count your electrons.
So like for this one, like what would an example of an isoelectronic species be?
Well, he gave you,
Would it be just another molecule that
has the same electronic
the
configuration.
same electron configuration?
Yes,
So
exactly.
something that has a carbon basically that has 1s2 2p6. would
These
that be the
guys
case?
have the same isoelectronic configuration because this oxygen is filling the role of this fluorine and hydrogen. You count your electrons.
But in the example above, wouldn't fluorine have a valence of 7 and then hydrogen have 1, and in the bottom example, oxygen only has 6? So how does that
You don't want to worry about these guys. You want to worry about the center one.
okay.
Like this guy's going to be 2s2. That's when he's happy. This guy's going to be 2s2, 2p6. This guy's also going to be 2s2, 2p6. All of these guys want to be the same. So it's like there's no point in saying it for this example.
Okay,
they're
so
all-
then by that methodology, so would methane essentially be isoelectronic to carbon dioxide too?
Yeah.
Okay, cool. Got it. Thank you.
Okay, no problem. Anybody got any other questions? No? You want to go over anything?
I have some questions
Uh,
on.
Oh, my bad.
Oh, you can go. You can go.
So I wanted to go over the molecule. I don't even know how to pronounce it. The M symbol,
Mulligan systems?
with regards to U and G specifically,
Oh, okay.
and primes.
Annie, I went with this with you
So
on
if we
Friday,
could go over
right?
example that involves that, that would be great.
Kinda.
Yeah, kind of. Oh, let me just pull up my notes. Pretty sure I posted my notes on Mulligan symbols. And I included the U and G. And that has more, it has to do with like, it has to do with the nodal stuff. So let me share this. Let me erase everything. All right. So for U or G, right?
Yes, U and G and the 2 primes. 1 prime, 2
Okay.
prime.
Okay, well, prime, you don't have to worry about too much. You're not going to go into it as that much, but I'll go over all the same. So for U or G, you have, I'll write an example of C with double bonded C and so, you know, in that whole stuff where it's like the positive area and the negative area.
Yeah.
So for U or G, it's just the difference between whether this guy, like, it's like this. We'll assume that the filled in area is negative. So if both of them are on the same thing, this thing is ungarred, unjured, or whatever, however you want to pronounce it. And basically you prove that by the inversion point. And if it flips over and it looks different, where like it looks like this, it's ungarred because it switches, the operation is inversed and this and the phase sign is switched. And that gives you the U subscript. Now, when it comes to the regular G subscript, you're going to take the same operation, but if this phase looks exactly the same when you inverse it, you give it the Gurade thing. And it looks exactly the same. Does that make sense?
Kind of. So is
Okay.
the yeah, sorry. Is the important thing here is the inversion center itself. So if a molecule or atom doesn't have an inversion center, then you can't apply Garrett or unGarrett to it, right?
Almost every molecule will have a inversion center, but it's like you have to first like determine whether or not you can do that by determining if it's A, B, E, T, 1 or 2.
I see.
So by definition, U is, you can find U through this through these methods. Does the orbital sign / shading, or is the orbital asymmetric with respect to the inversion operation? If so, use the U subscript. Or for G, does the orbital sign / shading stay the same, or does the orbital symmetric is the orbital symmetric with respect to the inversion operation? If so, use the G subscript. Does that make sense?
Yeah, got it. Yeah. I got
Okay.
it.
So for prime, you're not going to need it too much, but it has to do with sigmas. And I'm just going to have to erase everything here. And I guess I'll like post this on like a YouTube thing or something. I'll just make an announcement of it. So prime or double prime. Now in my notes, I use this very annoyingly overly complicated drawing. So here we have a C4 axis and C4 point symmetry. And here we have a sigma H and a sigma V. And sigma V here as well. Now for prime, imagine that there's a horizontal plane, sigma H, perpendicular to the principal axis of rotation, C4. If the orbital is reflected across this mirror plane, does the orbital change sign last shading? Is the orbital symmetric with respect to the reflection? If so, we use prime. For double prime, if the orbital is reflected across the horizontal mirror plane, does the orbital sign / shading stay the same? If the orbital is asymmetric with respect to the reflection, if so, we use double prime. Does that make sense?
Yes, it does. Thank you.
Okay, awesome. Anybody got any more questions? I'm going to take that as a no. So I'm going to pause the recording.
I didn't understand. He said that there's C2, but there's no C4.
Oh, well, there's, okay. So when he drew it, he kind of drew it in a shitty way. I'm not gonna lie. He should have probably drew it like this.
Wait, can you share screen again?
Oh yeah, sorry. He should have drawn it like this.
Oh, okay.
Does this make more sense?
Yes. And
Okay.
then why does it have a S for?
Because what was the reason again? Oh yeah. The reason why it's S4 is because you know what the rules are for S?
It's something like you rotate and then mirror.
Yeah. So if you like mirror this, we have, just imagine this is like a perfect mirror. Please don't judge me. So we have a mirror here. If we rotate it, we can make it look exactly like this. If we like rotate it slightly, like
Oh,
120
gotcha.
degrees. Yeah.
Wait, does it matter which order you do it in? Like mirror
I mean,
first?
not really.
Oh, okay, gotcha.
I mean, personally, I like to mirror first because that makes it a little simpler to conceptualize. But you could do it however you want. I don't know how your brain works.
Okay, and then also, he said something about if it's C3 and it has like a sigma H, it's automatically S3.
Huh?
I don't know. That's what he said.
Give me a sec. Thing closed. The S3 is automatically a C3 or
No,
something.
okay, so if it's C3 and it has a sigma H, it automatically has an S3. I think that's what he said.
So C3 and it has an H, that means it's an S3. Well, that's actually, I think you're overthinking it in this sense because like when I think C3, I think of planar boron, like planar, oh, God. I think of planar bora trihydride or whatever. Trihydrogen boride or whatever. Because I guess I'll draw it in a new perspective. So you obviously know that that configuration is C3, right?
Yes.
So if you draw boron, like say like this.
You're not screen sharing.
Ah, damn it. Oh, well, it's not like he's gonna watch this. Okay. Well, if you just, let's say you draw it like this, you can easily just mirror it and make it look exactly the same.
Yeah,
So that's what he meant. Simple as that.
Oh, okay, gotcha.
You guys haven't even gotten to the fun stuff yet. What else? Does that solve your question?
I think so, yeah.
Okay. Any other questions?
I have a question.
Shoot.
So I was wondering if we could go over chirality and how that applies to everything that we've been doing so far, because he didn't go into too much into it during class.
Well, chirality is just handedness. Okay. Okay, I'll give you a chiral example. Let's go back to that methane. Now, what would you say methane is? Is it chiral or is it achiral?
This is achiral because all the substitutions are the same.
Yes, yeah, exactly. Now, if I made it, if I change one of these hydrogens to like say a fluorine, now what is it?
It's chiral.
Yeah. Do you know why?
Yes, because not all the substitutions are the same, or is that not the correct logic?
It's because if you mirror it, like say your hands, let's say spontaneously one of your fingers is green. Now your hands aren't perfectly symmetrical. That means that if you rotate it, it's not going to look the same.
So does that mean it's achiral then?
Yeah, it's achiral
Okay, all right.
Go for it.
because the position is not going to be the same. This can be further elaborated in more complex structures and is probably easier to detect in more complex structures. Like, oh, okay, this is an even better example. Actually, that was kind of, wasn't exactly achiral, but you could definitely make it look the same. But let's say, oh, Cl, fluorine, bromine, and hydrogen. If you rotate it, it's not going to be the same. If you invert it, it's not going to be the same because all these guys have their own individual place.
Yeah.
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 So does that solve your question?
Part of it. I mean, I also wanted to see like how would this show up like on an exam question.
Well, have you looked at the practice exam?
I was gonna do that tonight, but then I remember you had office hours, so I decided to leave that for later.
Okay. Well, let's see. Well, okay, we'll just use the freaking office out. We'll just use the practice exam example.
That's
So here's, he gives you 3 examples. He gives you a planar example, an upright example,
The box is Yeah, but it's good. Like
which is your upright example, and your skewed example is this guy.
loses charge that much fast. Cool. I mean, yeah, if you're in the one, they use fast time, but like in big one, like recently I've been fast charging this.
So he's going to ask you for each confirmation, determine whether these are chiral or achiral. Let me just isolate this one a little better. So tell me for this one, is this chiral or achiral?
Would it be achiral?
Yes,
Why is that the case though? I kind of guessed.
because it's on the C3 axis and it has a horizontal mirror plane.
Oh, right. Thank you.
So just when you get these questions, I want you to imagine the molecule and then mirror it exactly.
So imagine the molecule in mirror. Okay. So would a good technique then be like literally just draw a line, imagine that's a mirror plane?
Yeah,
Yeah, and then draw it.
you'll be able to draw on your exam. So yeah, do exactly that. Now, anybody else want to tackle the rest of these? Or you could just keep going at it.
I don't mind keep going at it.
All right.
If that made sense.
Tell me, what is the upright one?
Would it be achiral as well?
For upright? Yes, you are correct.
Yeah, because again, it has a C3 axis, right?
Uh-huh.
And the horizontal plane. I
Mhm.
believe.
vertical mirror plane in this case, but
Oh, vertical mirror plane because it's not planar, right? And it's
Yeah.
all upright. Cool.
Mhm. All right.
Wait, sorry. Can you explain why the skewed is achiral again?
The skewed is not achiral, it is chiral.
Oh,
We're
okay,
talking
never
about the
mind.
upright one.
Okay, gotcha.
Daddy's home.
But could you tell me why the skewed one is chiral?
Like if you mirror it and like try to flip it back over, the wedge hydrogens would go the other way.
Yeah. You're correct. So does that help you?
Yeah, could you say that one more time? The explanation, I'm sorry.
So for planar, the reason why it's achiral, because the C3 axis and it can have a horizontal mirror plane. The upright is the C3 axis and it has a vertical mirror plane, which makes it achiral as well. Skewed has no mirror plane and therefore is chiral.
So automatically, if a structure or whatever it is has no mirror plane, then it's chiral.
Yeah.
Okay. Cool. Thank you.
Okay.
I have a quick question about the planar molecule.
Okay.
So for that one, the mirror plane that we're looking at would be like in the plane of the paper, right? Like there wouldn't be a vertical one.
You can imagine it however you want.
Because I'm just trying to, if it's a vertical one, wouldn't the hydrogens, like if you were to reflect it, wouldn't they not map?
Well,
onto it?
as long as you can create a mirror plane for it, doesn't matter if it's vertical or horizontal,
Okay.
it's achiral. If you can mirror it exactly in some way, shape, or form, achiral.
Okay, and then what if he were to give us like a question where he would tell us to draw symmetry elements? Would it just be like consider the OH as one entity, or would it be like this where there's two bonds?
Drop what?
Like if he told us to draw all the symmetry elements, would this be a possible structure? Do you know?
I'm sorry, I'm a little confused by what you mean.
Like if he told us to draw like the C3 and all the different elements.
Okay, yeah. Oh yeah. Like they're like if like it was OH and like chlorine and fluorine and all that stuff.
Yeah.
Oh, okay. Then they would all be like chiral.
Oh, okay. Got it. Okay, thank you.
Oh, actually, wait. You could find a mirror plane for them. Yeah, you could find a mirror plane for them by like through a horizontal mirror plane, like in the planar one. But they would basically all be, yeah. You wouldn't be able to. Upright would change to chiral, I do believe.
Why? Maybe I shouldn't be sitting here.
Got it. I was thinking about the vertical mirror planes.
Huh?
Like, can I annotate?
I'm sorry, you're cutting out.
Can I annotate really quickly?
Sure. How do I give permission?
It's okay. I just zoom. So like this wouldn't be a mirror plane, right? Because like the bonds of the OHs are different.
Yeah, I think he more wants it to be like boom, like that kind of mirror plane. Yeah, you got it.
Got it. Okay, just wanted to confirm. Thank you.
No problem. Any more questions, guys? Speak now or forever hold your questions.
I wanted, like, I've been wanting a cornices. I'll send you the link. Really? Yeah, it's really cheap.
Okay, so the whole question's on Vesper geometry. I just started recording again because I'm not used to this. Tough luck to anybody who is going to watch this.
Salmon.
Okay, we're just going to erase everything here. So when I did this, he asked for the structure of sulfur trichloride, trifluoride with a chlorine. So sulfur like this. I think this is the example he gave us, and then he asked us to draw it in any way we saw fit in the different ways that it could be in. So first I did my electron pairs. And then I got to work with the different shapes. So here's one way you could look at it, which is Cl. Fluorine, fluorine, fluorine. And then you have a little lone pair here. You could also draw it as such as this, where 120 degrees and 90 degrees. According to the structure, the bond angle of equatorial bonds are 120, and the bond angles between the axial and equatorial are 90, is 90. And then there's the final seesaw one, which was
Where did you get it from where? Oh, no.
where we have an angle of 107 and an angle of 173. And the shape of the seesaw is its seesaw shape or distorted tetrahedral. And since the lone pair is one corner of the VSEPR geometry, the geometry will warp to reduce the repulsion between the lone pairs and the bond pairs. Bond pairs tend to stay closer together than the lone pairs. And this results in different bond angles than predicted, and the shape distorts into a tetrahedron seesaw. These are the different kind of shapes. Does that make sense?
Oh,
Mhm.
So that's about as much in depth as you should get now, unless you take inorganic too. God bless your soul if you do that.
Okay, so he does want like, I guess like the most stable form and then the bond angles for it.
Yeah,
Okay,
but the bond angles are pretty like standard and don't really change unless it's like something really wacky, but he's not going to ask you for wacky.
hmm
Any more questions? I'm going to pause the recording.
When like you say, when the nearest city